Hi, this is Peng Wu from Futurewei Technologies. Today, I'm happy to share our journey to port V8, the JavaScript engine, onto RISC-V. So before I get started, this is really the joint work of three core teams. So there are three of us from Futurewei Technologies. We are all coming from compiler background, but have no prior experience with V8. And we started this work back in January. And there are the RIOS lab. We have a few students joining us from the very beginning. And in fact, we open sourced our code base in July. And at the time, there is another team independently working on another V8 for RISC-V port from the Institute of Software Chinese Academy of Science, the PLCT lab. So we actually open sourced the code bases around the same time. And once we see each other's code, we decided to join force together. So the PLCT lab is really a surprise collaborator for us, but the outcome is amazing. So let's first look at V8. So why do we want to focus on V8? If you look at the language toolchain landscape of RISC-V, you can see that support for static languages is pretty comprehensive. So there is Go, there is C++, there is Rust. But if you look at JIT languages, for example, Java or JavaScript, or for example, Dart or PHP, all of them are missing at least not a mature production level support for JIT languages. And among all these JIT languages, we believe JS is the biggest missing piece, because if you look at the web technology stack, essentially without JS, you don't have the web. And there is the client-side JavaScript represented by the browsers, and there is also the server-side JavaScript represented by Node.js. And in fact, Node.js is used in a lot of the web backend stack and used by a lot of these major companies. And in the browser space, actually, Chromium-based browser dominates the number of web pages being serviced. According to the Wikipedia statistics, about 70% of the web pages are serviced by Chromium-based browsers. And so both of them actually are supported by the V8 engine here. And in addition to JavaScript, in fact, V8 also supports WebAssembly. So WebAssembly is not only a very efficient form to execute native code on the web, but also is being explored beyond the web space into, for example, lightweight containers on the edge side. So basically, by enabling V8, we are supporting two languages and also the majority of the client side and server side JavaScript scenarios. So the goal of this project is the basic one is to first support a functional JavaScript engine on RISC-V, and eventually we want this RISC-V backend to be performant as well. And the basic requirements from the hardware side for supporting the full functionality of V8 is the RISC-V 64-bit G. So G represents IMAFD, and also the control register and fence instructions. So these are pretty typical setups. And note that the C extension, which is available on a lot of the RISC-V hardware, is a nice to have, but it's not necessary. So in our initial effort, we are focusing on supporting the basic functionality with just a G subset. And our initial target architecture is the High5 Unleash board, and we have Fedora running on top of that architecture. But eventually, RISC-V's strength is really, it's a customizable ISA. So we are going to support additional extensions such as the C extension, the B and J and P and V as they are ready and available. Let me first give an introduction on V8. So V8 was developed over a decade ago, and it has evolved into 2 million lines of code, primarily in C++. So it's a pretty well-architected and mature code base. It has supported all the major hardware platforms, including x86 and ARM. So RISC-V would be its latest addition. And in addition to that, V8 comes with a very comprehensive set of test cases. And these test cases actually are essential in terms of ensuring the quality of all the new backends. So let's take a look at how JavaScript executes in V8. There are two modes of execution. There is the interpreted mode going through this interpreter called the ignition engine. So this is primarily to optimize for startup time or for some devices with limited resources to minimize the memory footprint. But the majority of the code, for example, on the browser side, would be JITed, and that goes through the backend compiler called the turbofan compiler. And there is also the WebAssembly, which goes through the same turbofan compiler to generate target-specific code. So just one interesting aspect of the interpreter of V8, the ignition engine, is architected in a way where it's actually also relying on turbofan to generate target-specific codes. So this is quite unusual. So for example, in typical interpreter implementations, for example, like C Python, usually the interpreter itself is written in C, and it's in fact very easy to port the interpreter to a new platform as long as you have sort of the C compiler ported to the new platform, and just compile the interpreter, and then you have the runtime ported. But in this case, we actually don't have the shortcut because Ignition relies on the turbofan toolchain to generate target code instead of relying on the C++ toolchain. So basically, all our work is centered around enabling the backend piece of turbofan on RISC-V. One important decision we made early on during the development process is to decide to morph the RISC-V backend from an existing backend. And we chose MIPS64 because the two ISAs are quite similar. And so the first step of this process is what we call RINO, basically RISC-V in name only. It may sound a bit silly, but what we literally did is to find all the places where MIPS backend code are. They are actually neatly organized in like MIPS64 directories, and we just copy over all the files to RISC-V directory and change the name to RISC-V. So essentially, we got a working backend in the sense that it's actually generating MIPS64 code, but the workflow all look like it's targeting for a new backend. So that's the starting point. So before I explain how we develop a real RISC-V backend, let me first explain how the abstraction levels of the compiler works. And as in any compiler, the intermediate representation is the centerpiece of the compiler abstraction level. So in this case, the turbofan IR, which is shown in the middle of the picture, is where most of the compiler transformation optimizations are happening. In fact, turbofan support several levels of IRs. The highest level is closer to the JS semantics, so it's called complex JS operator. It's called operator in their terminology, and they are gradually lowered to the very low level called the simple machine operator. And these operators actually are very close to machine semantics. For example, it has like an IR that called int32 add, basically adding to 32-bit integer, and it can essentially be mapped into one machine instruction. So everything going from coming from the user side are essentially converted into the turbofan IR. So on top of turbofan IR, we also have like ignition bytecode and also some internal built-in functions, and all of those mostly are also lowered to the turbofan IR. And below the dotted line are the what we call the interfaces that are target specific. And those are primarily representing the machine instructions. So if you look at the bottom level called assembler API, so these are very close to what a machine instruction would look like. For example, for RISC-V, we have these API called add IW, which is the same name as the RISC-V add instruction, add immediate 32-bit, or BNE, which is branch not equal. And Turbo Assembler API is just a macro over the basic assembler where it encapsulates some of the common codegen patterns. For example, the call API represents the typical sequence to make a JavaScript call, or push for pushing multiple slots onto the stack. And essentially, the entire compiler works as like sort of flowing from top down and just lower gradually to the lowest level, which is the actual machine instruction. And so everything that is happening above the line are lowering that is machine independent. And for the backend, we don't have to care about that. But any lowering that crosses the dotted line are actually touching the pieces in the backend. And there are essentially two types of lowering crossing the line. One is the lowering from the simple machine operator to the turbo assembler API. So this happens in the code generator. And another piece is lowering from the built-in function. There is a special type of built-in function that is almost like a assembly code. And those ASM built-ins are directly invoking turbo assembler API. So those ones also need to be ported in the new backend. So basically, the new backend need to address those pieces highlighted in yellow. And so basically, phase 2 is what we call the minimal viable backend. We work from bottom up. Remember the previous picture, to gradually convert the sort of the MIPS instructions into RISC-V instructions. And we started off with the assembler. In fact, in the very first step, we actually kept the assembler API interface from MIPS. Just the implementation of these assembler is actually generating the RISC-V encoding. And gradually, we even later on changed the assembler API so that the code looked more and more like RISC-V code. And here, I want to explain another piece of V8 infrastructure, which is called a simulator. This simulator actually should not be confused with the RISC-V standalone simulator like Spike or even QMU. So this simulator actually is inside V8. What it does is that V8 has this special execution mode called simulated run mode. Basically, you could run entire V8 on the host machine, say x86, so the JIT and everything is on x86, but you can configure the JIT to produce code for a different target architecture, in this case for RISC-V. So when V8 is executing the JIT code, it will invoke this internal RISC-V simulator so that in this execution, you actually have a mixture of executing on x86 and also executing binaries from RISC-V. And this simulated run mode turns out to be a great productivity saver because we could have our entire development workflow on x86, and we could have more tools to debug because there is a rich trace mode from the internal simulator. And also, because we can then set up our CI entirely on a general purpose machine. So here we give an example of like how the lowest level, the code assembler look like. And you can see it looks very much, very straightforward. So we're implementing add instruction, sub instruction, SLL, and the encoding is reflecting the RISC-V encoding. And similarly, to the right-hand side, we show the code for the simulator. Basically, it's a pretty straightforward decoding of the opcode and then implementing the functional semantics of these operations. With phase 2, we get a fully functioning V8 engine, but the performance is not optimal. So phase 3 is really about refining, refactoring, and optimizing the generated code sequence. Right now, we are under phase 3. So next, I'm going to give some demos. There will be two configurations we want to show. The first configuration is running on x86, but using the simulated run. And the second configuration is running on the actual board. And so for the first set of demos, this one is a very simple demo on generating two RISC-V instructions running in the simulated run, and which basically these two instructions are adding two numbers. So adding AB0 with C, and the result should be ABC. So here we are. This dash trace theme is dumping the instructions executed by the simulator. As you can see, there are two instructions here. And we also show the sort of the target result in the register. So it's pretty rich trace. And next we bring up the D8 shell, which is an interactive shell for V8. You can pretty much type anything into the shell, like defining a variable and print hello world. Okay, this is all running on x86 using the simulated run. Just to show the trace from this, we repeat this experiment with tracesim flag. And now you will see the RISC-V instructions being executed. There are a lot of them. So here you can see actually to the right-hand side in the parentheses are the dynamic instruction count. And you can pretty much use this trace to debug. Okay, and the next demo is actually running on the actual board. So here we're demoing Node.js and NPM. So to the left-hand side, we define a simple NPM package, which is it's called app.js. So the app is defined to the right-hand side. And there the basic behavior is to receive a request from a client, and which is in the form of a form, and we parse the form and then generate an HTML, send it back to the client to render on the browser. And notice that to the left-hand side, the app also has some dependencies. So NPM server would also install the dependencies here. And I want to point out that actually this demo is set up and recorded by our colleague from the PLC team. In fact, Yahan has single-handedly initially brought up Node.js using our V8 setup. So thanks, Yahan, for the work. So here, this is Yahan's board, RISC-V board. You can see from the CPU info. And he's executing npm install. And there it will install the dependencies. And he is going to launch our own web application. And the application is listening at the port. And now he's switching to his desktop. And here he's inputting his name into the form. And the rendering is actually the result sent back from the server. Okay, so Node works, NPM works, so it's cool. All right, so we just want to show that it's not just some demos that are working. We actually thoroughly tested our RISC-V backend using the test cases coming from V8 as well as from Node. So now we are passing the majority of the V8 and Node test cases, and we actually compare with the ARM backend, which is also sort of embedded backend, but it's supported by the official Google team. And we are also able to run the GS benchmarks that V8 is tracking, SunSpider, Kraken, and Optane. And we also tested on different configurations, including the bug build, release build, and also the real board and the simulated run and QEMU. So all of them are passing. And you can actually find out the latest testing results from our GitHub wiki. Now that you have a good idea of where we are, let's step back and look at the past 7 months and look at how we get from knowing nothing about V8 to today bringing up Node and NPM on RISC-V. So our approach of morphing from an existing backend seems to work very well to bootstrap our whole process. So in fact, Rhino only takes like 2 weeks to complete. And then we added the simulator in April. And then later on in July, we open sourced the simulated run of V8, which already passed most of the V8 test cases. And looking back, in fact, we realized our early realization that debugging is the biggest challenge instead of development has guided several of our key development strategies. So for example, our use of embedded simulated run instead of going straight to the native board has saved us a lot of time. We leverage the rich set of test cases and especially focusing on exposing bugs in the simpler test cases also saved us a lot of time. And we have also invested in tools, for example, to analyze the traces generated by simulated run and compare it against the traces from MIPS has also been a great productivity saver. One thing I want to point out is that in the beginning, we have decided that simulated run would be a good indicator of the quality of the backend. And we believe that going from the simulated run to a native run would be a small step. And in fact, that is the case. So basically, 3 weeks after the open source, we were able to pass most of the V8 test cases in the native run. And I think within a month, we were able to bring up Node.js. And last point we want to point out is that open source really fostered like sort of unexpected collaborations and has significantly sped up the progress. In fact, the step from simulated run to native run, we relied a lot on the PLCT team's expertise in working with the QML and native board. So it has significantly shortened the time between these two steps. And in fact, right now we're working on upstreaming, collaborating with the Google V8 team, as well as releasing Node and V8 onto a stable Linux distribution for RISC-V. So on that front, in fact, the Fedora community member had helped us to build a binary for Node.js. And so basically, we have these helps from the community and everybody is chipping in with their expertise. So it's a great story. Just in summary, right now the project is out there, it's on GitHub, and we have about 10 committers, and the backend consists of like over 300 commits, and we have documents to help people to get started if you would be interested in contributing. And we have Slack channels and bi-weekly community meetings. All of these are open to anyone to join. And right now we are just discussing on the upstreaming and officially releasing the V8 and Node into the community. So in terms of roadmap, our immediate next step is to prepare for the V8 upstreaming and releasing Node to Fedora. So this would happen in the next a month or two, depending on their release schedule. And for the rest of the work, we have almost done with phase 1 and phase 2. We are solid into phase 3 enhancement. There are 2 pieces of work that's ongoing. One is code gen optimization. The other is to adding support for the C extension, the compact instruction set. And we would like to be engaged with the community on the other extensions. So for example, we have our eye on SIMD and vector extension support because those are especially important for the WebAssembly front end. But we are waiting for the community to be ready with the other tools to be ready. And finally, I want to say something about the research. Although V8 RISC-V right now is pretty much a development project, keep in mind that this is actually the first major JIT engine being ported into RISC-V. And with these groundwork being done, I think now research is within the realm of reachable realm. So we welcome researchers to come join in and play with the code base and experiment with new ideas. So I cannot conclude without thanking the community and the contributors. So here we have listed everyone who has participated in contributing into the code base, joining our Slack discussions, open issues, and attend our community meetings. So we do welcome anyone who is interested to come in. Yep, that's it. Thanks for watching, and we're really excited. I think this is just the beginning of the more exciting journey of doing more research in terms of enabling more advanced features or even software hardware co-design on the RISC-V. And we also welcome people who have ideas of like compiler optimizations to produce more efficient code for this new backend. So yeah, you can find us on GitHub, on Slack, and we look forward to hearing from you. Thank you.